Okay, good morning or afternoon, ladies and gents. So for today's lesson, we're going to build a little bit more on what we've done previously about adding and subtracting vectors, in this case looking at vector components. So the aim for this lesson, we want to recall vector addition and subtraction to complete in both Cartesian and polar form. Surprisingly, this will not be as difficult as the actual vector addition or vector subtraction. So, with all due respect, you need to recall that if you've got two vectors going in certain directions, they will obviously create a third vector, sorry. So let's just say if you've got vector A going in a 45-degree angle, vector B going at a 0-degree angle, we know that if we add these two vectors, we will get a third vector C. A plus B equals C. We also know with respect to this, that if we do the opposite for vector subtraction, A minus B, it is the same as A plus minus B. Therefore, if this were the case, minus B would still have the same angle, but it will be going in an opposite direction. So in this case, A at 45 plus B plus minus B, equals A minus B. So for the first thing we need to do, we need to actually sketch out, we need to actually sketch out some of our vectors. There's that good footing. Gotta love having a weighty phone. So in this case, if we provide you with three separate vectors, A at the 90-degree angle, B at 0 degrees, C at 45 degrees, D at negative 60 degrees, and E at negative 90 degrees, how could we add or subtract them? Well, all we have to do is quite literally connect the vectors. If we had A plus B, we start at A plus B and show A plus B. D plus A, start at D, go to A, D plus A. C plus E, go up to C, down to E, C plus E. Vector addition is surprisingly not that hard. And, of course, keeping this in mind, neither is vector subtraction. C minus A, up to C, the opposite of A, C minus A. For C minus E, up to C, opposite of E, C minus E. And then finally, minus D minus B, think of these in reversed orders. Minus D minus E gives us minus D minus E. So if you were asked a question to literally sketch the following, it shouldn't be that difficult. You start with the very first vector represented, and then just simply add or subtract the second one there. So building on this, when finding the sum and difference between Cartesian vectors, key words here, Cartesian vectors, you simply add or subtract the x and y components respectively. So we know that when we do have a vector in the Cartesian form, regardless of whether it's written in trilling, x and y, matrix, or I and j components, it still represents an x and y value. So, for our first example, if vector A is represented at 2 at 3, and vector B is represented at negative 4, find A plus B. For this one, because we're trying to find a mathematical answer, we're not required to draw it. You are more than welcome to, and it will never, ever do you wrong by drawing them. But because we just want to add these together, what we want to show, let's try that. What we want to show is our x component for A plus x component for B, followed by y component for A plus y component for B. Just add them together. So in this case, 2 plus negative 1, then 3 plus 4, which just gives us A plus B at 1 at 7. That's all it is. So keeping this in mind, if we had another set of vectors using our I and j components, if A is at 2i minus 3j and B is at minus I plus 4j, find A minus B. For this one, you're going to see I've written these a little bit differently, but when we get to our complex numbers, this is going to bring back some brilliant memories for you. What I've done for A minus B is I've taken the I and j components outside the brackets. This means there's less chance of mucking around here. So for our I component, it is the x component of it A minus x component B, plus for our j area, y component A minus y component B. So for I, it is 2 take -1. For j, -3 take 4. This then gives us a vectors A minus B at positive 3i minus 7j. Easy peasy. For our final example for this one, let's just move this a little bit. There we go. So there's just less shade to see. If we had them in matrix form, or we had one of them in matrix form, this one's a bit trickier. If A is represented at -3, 4, and B is represented at -3, 5, find A minus B. So for this one, we need to do a little bit of rearranging. We know that for anything in matrix form, the top point is X, the bottom number is Y. So we should be able to know that when we are subtracting these two vectors here, we could rearrange it so it is just XA, YA minus XB, YB. We can then bring these down. XA minus XB at YA minus YB. Substitute our values, get our answer, 0, -1. So like I said, because we're not trying to actually represent the vector in the Cartesian form itself, we don't need to draw it up. We are simply trying to calculate the vector addition or subtraction for Cartesian vectors. Moving on, however, when finding the sum or difference between polar vectors, you need to convert your magnitude and direction into x and y components. And you need to do this every single time. The maths for this is a little bit lengthy, but we've done this a few times before, so it shouldn't be that unfamiliar for you, and therefore it should be quite efficient to work through. So, if vector A is at a magnitude of 3 at the direction of 40 degrees, and B has a magnitude of 5 in the direction of -100 degrees, find A plus B. So we know that this one's going to be A. If we want to put A into its x and y components, we need to find our certain values. So we've done the maths before. Magnitude, cos of angle, and then magnitude, sine of angle. We know this. And again, big hint, we'll be using this for complex numbers. Plug in our values. Our magnitude is 3 for both of them. Our angle is still 40 degrees. We just have cos and sine because we're working out our specific x and y component. So in this case, our x and y components for vector A is 2.298, 1.928. For vector B, we know it's got an angle at -100 degrees, so it means it's going to be in the third quadrant. We cannot use this because it's not a perfect triangle. But we know from our straight line, it has a total angle of 180. Take away 100, you've got 80 left. We've now got a triangle we can work with. We have a magnitude of 5. So we know that when we substitute this into our components, our magnitude's 5, our angle is 80. The thing is, because we are trying to find our x and y, we need to make sure we're using our right trigonometric ratios. So because we're looking at the adjacent for x, it's going to be cos. Because we're looking at the opposite for y, it's sine. So 5 cos 80, 5 sine 80. In this case, 0.868 and 4.924 respectively. One thing to remember for B, because it's in our third quadrant, we know that our x and y values have to be negative. So that means that our answers must also become negative. Therefore, when we're showing the addition of these vectors a plus b, just like we did previously, x component of a plus x component of b, y component of a plus y component of b. Add the two sets of values together, get our numbers. Now to convert back into polar form. We know the magnitude for this is just going to be using Pythagoras, the square root of x squared plus y squared. In this case, it is our numbers together, giving us a magnitude of 3.391. We know how to find our angle. Inverse tan y over x, or the absolutes of y over absolutes of x. So inverse tan 2.986 divided by 1.43 equals negative 64.485 degrees. Remembering the quadrant it's in for us, we have to include that negative value. Therefore, a plus b in our polar form magnitude and direction, it has a magnitude of 3.319 at the direction of negative 64.485 degrees. And that's all she wrote. So ladies and gents, good luck for your next set of questions. I'll chat with you soon. Thank you very much.